Ethereum is more than a digital coin. It is a shared computer network that can run programs without a central owner. In this video, you will learn how Ethereum works. We will cover the blockchain, smart contracts, validators, fees, and why this system matters. Think about this. Most apps run on company servers. Ethereum is different. It lets many computers agree on the same data and the same program results. Let's start with the foundation. Ethereum is a blockchain. A blockchain is a public record shared across many computers called nodes. Each node stores a copy of the network's history. When new transactions happen, the network updates that shared record. On Ethereum, a transaction can do more than move money. It can also trigger code. That is the key idea behind Ethereum. It combines a blockchain with programmable logic. Let that sink in for a moment. That programmable logic is called a smart contract. A smart contract is code stored on the blockchain. It runs when someone sends it a transaction. The contract follows rules written by its developer, and every node checks the result. For example, a smart contract could hold funds until certain conditions are met. It could issue a digital token. It could also support lending, trading, or voting systems. The important point is this: the rules are executed by the network, not by one company. Now let's look at how Ethereum keeps all of this consistent. Ethereum uses a consensus system called proof of stake. Since 2022, Ethereum has relied on validators instead of proof-of-work miners. Validators are participants who lock up or stake Ether, which is Ethereum's native cryptocurrency. In return, they help propose and verify new blocks. A block is a batch of transactions. Validators check whether transactions follow the rules. If the network accepts the block, it becomes part of Ethereum's history. If a validator behaves dishonestly, part of its stake can be taken away. This penalty is called slashing. Here's what's interesting. Proof of stake is designed to reduce energy use compared with proof of work because it does not require large amounts of competitive computation. Now let's talk about Ether, often called ETH. ETH is the native asset of Ethereum. People use ETH to pay transaction fees and interact with applications. It is also the asset used for staking in the proof of stake system. Those transaction fees are called gas fees. Gas measures the computational work needed to process an action on Ethereum. Simple actions like sending ETH usually need less gas. More complex actions, like running a large smart contract, need more. Users pay for gas in ETH. The total fee depends on both the amount of gas used and the gas price. Since the Ethereum upgrade known as EIP 1559, part of the fee is typically burned, meaning it is removed from circulation, while another part can go to validators. Let that sink in for a moment. Next, we should talk about the Ethereum Virtual Machine, or EVM. The EVM is the environment that executes smart contracts. You can think of it as Ethereum's shared computer. When a contract runs, nodes use the EVM to compute the same result. This helps the network stay synchronized. Developers usually write Ethereum contracts in languages such as Solidity, then compile that code into bytecode the EVM can run. Because the result is checked by many nodes, the code must be deterministic. In other words, given the same input, it must produce the same output. That requirement is essential. Without it, the network could not agree. Now let's connect this to real-world use. Ethereum supports decentralized applications, often called dApps. These are applications whose core logic runs on smart contracts. Examples include decentralized exchanges, NFT systems, blockchain-based games, and lending platforms. But Ethereum also has limits. Transactions can become expensive during heavy demand, and smart contracts can contain bugs if they are poorly written. Once deployed, changing them may be difficult. That is why audits, careful design, and security research matter so much. Scientists and engineers are still improving blockchain systems, including Ethereum's scalability. One important approach is Layer 2 networks. These systems process many transactions outside the main Ethereum chain, then settle results back to Ethereum. This can increase throughput and reduce costs while still relying on Ethereum's security. So, what are the main takeaways? Ethereum is a blockchain that stores both transactions and programmable code. Smart contracts let people build applications without a central operator. Validators use proof of stake to agree on new blocks. ETH pays for computation through gas fees, and the EVM gives Ethereum a shared execution environment. In short, Ethereum works by combining distributed record-keeping with network-verified software. That combination is what makes it different from a simple payment system. As blockchain technology evolves, Ethereum remains one of the most important examples of programmable decentralized infrastructure. Understanding how it works is a strong first step towards understanding the wider world of Web3. This mini course was researched using these sources. Thank you for watching and keep learning.